Okay, let's talk a little bit about forces. We know that with Newton's first law, we have this concept of inertia, that nothing happens without some kind of push or a pull. Formally, that is, objects at rest tend to stay at rest, objects in motion tend to stay at motion unless acted upon by an outside force. And that force is just quite simply force equals the mass of the object times the acceleration. Okay? So if you have an object that is at rest and then it is no longer at rest, it is then accelerated. And in order for that to accelerate, we have this force of friction. And keep in mind that the key term here is accelerate. That does not mean that things cannot move. If you have a car that is moving at a steady speed at a constant rate, it can be good, like say we're going 60 miles an hour down the freeway, we're not turning, we're not speeding up, we're not slowing down, there is no acceleration. That does not mean that there are no forces. It means that the forces are balanced. So another way of saying that is that the net force is equal to 0. A good way of imagining this is, let's suppose I have a pen sitting here on my whiteboard. Now, what are the forces acting on my pen? Well, first of all, gravity is acting on the pen. So we've got the force of gravity here. And what else? Well, we've got the force of the table pushing back on the pen. If the force of gravity was not balanced here, there'd be nothing stopping this pen from going all the way through the table, all the way through the earth, and down into the center of the earth, right? That doesn't happen, so there must be another force. And you can call it whatever you like, the force of the table, force of the whiteboard, or whatever. But in general, we have force normal. And the normal force here is just that force that is perpendicular to the force of the table. And these are in balance. So whatever this force is, it is going to be 0. Now, a very common mistake that students make is they see the force of gravity is going to equal the mass times g. G here is approximately 9.8. And that's just relative to the surface of the Earth, and it will depend where you are on the Earth. It will depend on your altitude. If you go to different planets in the middle of space, this will be different. So this number only really applies close to the surface of the Earth, and not just the surface, but it really just applies to sea level, right? And so this will change. For most purposes, I go ahead and I round G up to approximately 10. It's an approximation. It works great for most things, and it simplifies a lot of our problems. Now, for friction, we have an object. This is called a free body diagram. We have some sort of applied force this way, usually, and we have some sort of force of gravity. And then we have force normal, okay? And this is, again, this is the force pushing back from the surface, right? So if our surface is here, right, this force normal is the surface pushing on our object and counterbalances gravity. If it's a straight line like this, and it is opposite. If it's at an incline, then it will be still perpendicular, and the math gets a little harder to do. So for right now, we're just going to focus on a straight line surface like this. And we have some sort of friction. This is our force of friction. Now, our force of friction is in two parts. It depends a little bit on the mass of this object. Heavier objects are going to have more friction. And it depends a little bit on the surface that we're talking about. More slippery things are going to have less friction. More sticky things are going to have more friction. So we have the coefficient of friction, and we're going to multiply that by force normal. Okay, and that is going to equal our force of friction. Let's do a problem where there's multiple forces. A 30-kilogram object was pulled to the left with 200 newtons of force and to the right with 500 newtons of force. What is the acceleration on the object? If we're stuck on this kind of problem, the first thing we should do is draw a picture. So it can be a simple picture. There's my fancy looking object. On this way is going to be 500. On this way it is going to be 200. Okay? And right here in the middle, I'm just going to say 30 kilograms as the weight of the object. So our net force is going to be 500 minus 200, which equals 300. Okay, so that's the total amount of force. We've got 500 newtons going one way and 200 newtons going the other way. So our equation is going to be force is equal to mass times acceleration. And this is if we're looking for acceleration. So our force is going to be 300 equals our mass, which is 30, times our acceleration. Divide both sides by 30. And our acceleration is going to equal 10. This will be in meters per second if we have the SI units. For a problem like this where there are even more forces than one, then all we have to do is add up the different sides of the equation and solve. So again, going back to our simple picture, we have 1, 2, 3, 1, 2, 3, and we have on the left, we've got 100, we've got 150, and we have 75. And on the right, we have 25, 35, and 175. So when we've got lots of forces like this, we're just going to add them up. So 150, 250 plus 75 is 325. And this is going to be 25 and 175 is 200, so that's 235. All right, so just like in our previous problem where we had two different forces, we're just going to subtract that, and our net force is going to equal 90. From there, it is just going to be 90 equals our mass times acceleration, which in this case is 50. 90 divided by 50 is going to be 1.8. Okay, this problem is slightly more complex. It's got sort of two different parts to it. A 1,500 kilogram truck was going 40 meters per second. The truck hit the brakes. The force of frictions from the brake was 250 newtons. How much distance did it take for the truck to stop? Okay, so we're looking for distance. We have an initial velocity of 40 meters per second. We have a final velocity of stop, which is 0 meters per second. And in order to get distance, which we don't know, we're also going to need acceleration, which we don't know yet. We have one more piece of information, two more pieces of information. We have the mass of the truck, which is 1,500, and we have the force of the brakes, which is 250. Okay? So with that piece of information, we can then solve the problem. So the first equation that we need is force is equal to mass times acceleration, which is going to be 250 equals mass, which is 150 times acceleration, divide both sides. The acceleration here is going to be 0.167. Okay, so now we have the acceleration. We need a way of figuring out what this distance is going to be. So we need a new equation. From previous work, we know that our final velocity squared is going to equal our initial velocity squared plus 2 times the acceleration times the distance. Final velocity is going to be 0 squared, which is 0. And our initial velocity is going to be 40 squared plus 2 times 0.167 times our distance. 40 squared is 1,600 equals 0.33 times our distance. We're just going to multiply through here by 3 to get this all sorted out, and that's going to be 4,800 meters equals our distance. So clearly he needs some better brakes if it's going to take about 5 kilometers to stop, but that's what we have for this particular problem. So this requires 2 steps. It requires figuring out what the acceleration is. Anytime you have a distance and acceleration problem, that's one of the pieces, and we have a force. So it requires kind of thinking, what do I have, what do I need? Algebraically, this is a fairly simple one, but conceptually, it can be challenging. This problem deals with the coefficient of friction a little bit more directly. So let's try this one. What is the minimum amount of force required to move a 600 kilogram object if the coefficient of friction is 0.4? So again, if we ever not sure what to do, then we'll just draw a picture. So we have our free body diagram, 600 kilograms here in the middle. And so what are the forces acting on it? We've got the force of gravity coming down here like this, and we've got force normal. Force normal is just the force that is acting sort of, in this case, opposite to the force of gravity. It's keeping whatever this object is from being pulled down to the center of the earth, right? So if it's something on a table, then it's the force that the table is putting back on the object, right? And the reason that's important is because we have a force of friction here. And our equation for the force of friction is going to be this coefficient of friction, called mu, times force normal. So what is mu? Mu, like I said, is the coefficient of friction. This is a number that modifies this force normal, and it tells us how big the friction is. Something that is very rough, has a lot of, is kind of sticky, has a really good amount of friction, like say rubber or concrete or something, then that's going to have a much larger coefficient of friction compared to something that is very slippery. So like ice or snow or something like that. That has a very low coefficient of friction, right? And we multiply it by force normal because force normal is telling us about the force that is coming off of this surface, right? And so these two things are related. So how do we get force normal? Well, we know that the force of gravity here is going to be mass times the acceleration due to gravity. So the mass in this particular case is 600, and the acceleration due to gravity is about 9.8. I'm going to round up to 10 just to make life easier for me. And we know that the force of gravity on this is going to be 6,000 newtons. Okay? We also know that the force normal is going to be equal and opposite to that, which is also going to be 6,000. And we know that the force of friction here is going to be this coefficient of 0.04 times force normal. So this is going to be 6,000. 6,000 times 0.4 is going to equal 2,400, right? And that's going to be your answer here. You have to put a minimum of 2,400 newtons of force on this object if it is going to move. Here's a slightly more complicated problem. We're going to be looking at the mass of the car. The car is driving at a constant speed of 30 meters per second. The engine creates a steady 100 newtons of force. The coefficient of friction between the car and the road is 0.3. What is the mass of the car? So the important bit of information here is actually not this 30 meters per second. It's actually this constant speed comment. What is the constant speed? The constant speed means that there's no acceleration. If there's no acceleration, then the forces are balanced. So what does that mean exactly? So let's have our car. Here again, my fancy picture of a car. We have some 100 newtons of force, right? This is just the engine doing the minimum amount to overcome whatever friction there is on the road. And we're going to go the other direction here. So this force of friction has to be 100 newtons of force, right? Because the forces are balanced. They have to be equal. If one was more than the other, then you would have some acceleration. But in this problem, we are saying that there is no acceleration. So we know that those are balanced. Okay? So now we need to know the mass of the car. So what is our equation? Our equation for the force of friction is going to be the coefficient of friction times force normal. Force normal is going to be, in this case, because the surface is flat, mass times the acceleration due to gravity, which is 10. Again, some people use 9.8. I'm going to round up to 10 just to make my life a little easier. All right, so another way of saying the force of friction here then is it's mu, the coefficient of friction, times the mass times the acceleration due to gravity, which is 10. Okay, as we've already said, this force of friction has to be 100. So that's going to be 100 is going to equal the coefficient of friction, which in this problem is 0.3, times 10, times the mass of the car, which we still don't know. But we can figure this out now from algebra. 0.3 times 10, that is going to be 3. So 100 equals 3. We divide both sides by 3, and the answer is going to be 33.3 kilograms. So kind of a toy car there. Right? So that one's fairly simple, but kind of have to understand this key concept about constant speed, meaning that these forces are equal, and that's how you're going to relate kind of an applied force from the engine to this force of friction this way. Okay, so the next problem, problem number 11, is what if there is some acceleration? So we've got this acceleration right here of 3 meters per second, which means that unlike problem number 12, those forces aren't equal. So how do we sort that out, right? So at the end of the day, we're looking for mass, and we have some givens. We have some sort of applied force of 30 newtons, and, well, that's it, right? That's all we're given. So how can we figure that out? So again, we're going to draw a picture. So here's my picture of a sled. Isn't it beautiful? So we have some 30 Newton force pulling this direction. And we have some friction here. Coefficient of friction is going to be 0.6. So we have some sort of force of friction here. So like similar sorts of problems, we have to combine these two forces. And whatever the force of friction is, it's going to be less than our applied force, obviously, because we have some acceleration. So we have to subtract this force of friction from whatever force is being pulled here. So we're going to set that up. So it is our 30 newtons minus our force of friction. And that's going to be our total force. Our net force is what we call it. So our net force is going to be 30 minus our force of friction. Well, we need a better equation, so let's do our net force is going to equal our mass times acceleration. Now we're getting somewhere. So our mass, which we don't know, and our acceleration is times 3. Okay, so how do we figure out what our force of friction is going to be? Well, like we said in previous problems, that is going to be, our force of friction is going to equal the coefficient of friction times the mass times the acceleration due to gravity, which is 10. So you can sort of see how we're going to solve this problem now. So our coefficient of friction is going to be 0.6, and that's going to be times 10 times the mass. It's going to equal 3m. Okay, so we still have some unlike terms here. We can't go straight to dividing things out yet. So let's go ahead and clean this up a little bit. So we have 30 minus 0.6 times 10 is going to be 6m, is going to equal 3m. Okay, now we're going to combine our like terms. That's plus 6m here, plus 6m here. It's going to be 30 equals 9m. Divide both sides by 9, and we're going to get 3.33. Okay, so that's going to be algebraically a little bit more tricky for some students. it's definitely hard if we don't quite understand that this is algebraically what our net force looks like. Okay. Okay, this is going to be a fun one for people who have ever had to drive around in the snow. So a 750 kilogram truck is driving at a constant speed of 35 meters per second. The coefficient of friction between the car and the road is 0.3. The truck hits an icy patch and the coefficient of friction drops to 0.1. What is the acceleration of the truck? There are actually quite a few different ways of solving this problem. I'm going to solve it one particular way just so that you can see how the different forces are kind of playing together, but that's not to suggest there aren't other ways of solving the problem, valid ways. So I want to start with recognizing this constant speed bit, right? What is constant speed? Well, like before in the previous problem, that means our force of friction is going to have to equal our applied force, right? If those things were not equal to each other, then there would be some acceleration. Okay. So we actually don't really need this 35 meters per second. We just need to know that this is what our acceleration is going to be, or what our forces are going to be. So let's figure out what the force of friction is, because that part we can figure out. So we have our truck, and that's going to be 750 kilograms. Our force of gravity is down like this. Our force normal is over here like this. And our force of friction is this way. Okay? So what is our force of gravity? That is going to be 750 times the acceleration due to gravity, which is 10. And that's going to equal 7,500. That's going to be the same as our force normal, 7,500. And our coefficient of friction is going to be 7,500 times 0.3. 7,500 times 0.3 is going to equal 2,250. So we know that the force of friction is 2,250, and we know that under this circumstance, call this part 1. In part 1, those two forces are balanced, 2,250. Okay? But there's a different part of this, right? We have part 2. In this second circumstance, we have the same amount of force, only the coefficient of friction on our road has dropped. So let's find out what the new acceleration is going to be. So similar to a previous problem, we're going to go, our force is going to be 2,250 minus our coefficient of friction, which is 0.1, times the mass of the car, which is 750, times the force of gravity, acceleration due to gravity. Okay, this is our force of friction. Is going to equal the mass of the truck, 750, times the acceleration, which is what we're looking for. Now, some of you will have noticed that we've got the mass in a couple of different places. If you've kind of understood this algebraically, you could have probably simplified some of this, but I want to show you how our total net force is going to be put together in this way. So this term is all about our force of friction. Combined with our previous answer, this is going to be the total net force. And the total net force is going to equal the mass times the acceleration. So let's do some simplification. So it's going to be 2,250 minus 0.1 times 10 is 1, which is going to be 750 just by itself. If we combine those two things, we're going to get 1,500 equals 750 times A. Divide both sides by 750. And A is equal to 2. So, and this will be in meters per second. So, squared. So the acceleration on this car is now going to be 2 meters per second squared. I'm sure, hopefully this is not a scary event for the passengers and the drivers, but that's the acceleration now. Okay, this one is probably one of the more complicated problems, so we'll go ahead and end it here after this particular problem. A 1,500 kilogram truck is going 35 meters per second, sees a deer in the roadway 50 meters away. It slams on its brakes to avoid hitting the deer. What is the coefficient of friction on the road in order to miss the deer? So anyone who's kind of driven in deer country knows just kind of how awkward that can be. All right, so in this case, we do have some sort of acceleration, but we don't know what that is yet. And we want to know what the coefficient of friction is, which we aren't given. And so what other things do we know? Well, we have the mass. That one's kind of easy. We have 1,500. And we have an initial velocity of 35 meters per second. So he's going pretty fast down the road. Our final velocity is going to be 0, right? Because he's got to stop to avoid hitting the deer. All right. So how can we figure out what our acceleration is going to be? Because in order to figure out what our force of friction is going to be, we are going to have to know the mass and the acceleration, right, in order to determine all of that sort of thing. All right, so let's go with coefficient of friction times force normal, and we have force is equal to mass times acceleration. We're going to need those. We're also going to need, again, from our earlier in the unit, final velocity squared equals our initial velocity squared plus 2 times the acceleration times the distance, and we need to figure out what this acceleration is. We need to figure out what that acceleration is so that we can figure out what the total force has to be placed on this truck in order to slow it down, so that we can figure out then what the force of friction has got to be. So again, let's go ahead and solve this. This is going to be our final velocity of 0 squared is going to equal our 35 squared plus 2 times the acceleration, which we need to figure out, times 50. So 35 squared is going to be 1,225. It's going to equal 2 times our times 50 times acceleration. You might notice that this is going to be negative, which makes our acceleration negative, which makes sense. But for a problem like this, it's not something we need to worry about over much. This mostly just tells us what direction things are happening in. So 2 times 50 is 100. This divided by 100 is going to be 12.25. All right, so we need a minimum acceleration of negative 12.25. Okay, so what amount of force has that got to do? So our force is going to equal 1,500 times 12.25. This gives us a total value of 18,375, and that is going to be in newtons. All right, so the total force of friction has to equal this. All right, so if we can apply this much friction to the car, it will slow down in time. So let's set that equal to the coefficient of friction, which we don't know yet, times the mass. Some of my more astute students in algebra will notice we put the mass already in this equation, so we're just going to cancel that mass out, which gives us another avenue of solving this problem with fewer steps. But again, I want to go through these steps a little carefully, make sure we don't miss anything. And then this is going to be times 10. Again, coefficient of friction times force normal is going to be, force normal is mass times acceleration due to gravity. So that's where all of these numbers are coming from. So our coefficient of friction is going to be 18,375 divided by 15,000. which gives us a coefficient of 1.225. All right? So that is what the coefficient of friction has to be in order to slow this truck down, in order for it to stop before it hits the deer. Yay, Bambi. All right, I hope this is helpful in kind of sorting out how to think about some of these problems. Let me know if it helps.